Hi everyone, the subject for this video is what I say is working with graphs in the reverse direction, and so what I mean is finding velocity from a graph of acceleration versus time, and finding displacement from a graph of velocity versus time. This is going to be a little bit tricky, but the really important part is going to come at the very end when we derive an important new equation. So be on the lookout for that. That's going to be kind of the thing to cap off the 3 videos that have all been about graphical methods. So, displacement is the net area under a graph of velocity versus time plus the initial displacement. Instantaneous velocity is the net area under a graph of acceleration versus time plus the initial velocity. And we now have all the tools that we need to produce any graph of displacement, velocity, or acceleration from any other graph. Under constant acceleration, the net displacement over the time interval from t0 to t is given by x minus x0 equals v plus v0 divided by 2 times t minus t0. The way that I like to interpret this is the net displacement equals the average velocity times time. And I'll explain that a little bit later. But I should emphasize, this only works when we're undergoing constant acceleration. Okay. So let's determine displacement from a graph of velocity versus time. We know how to graph velocity using a graph of displacement versus time, but what about working in the opposite direction? Can we use a graph of velocity versus time to find displacement? Yes, we can. To do so, we need to find the net area between the v of t curve and the horizontal axis, which corresponds to v equals 0. Up to the time in question, and then add whatever the initial displacement was. So by net area, I mean areas above the horizontal axis are taken to be positive, and areas below the axis are negative. And so I'll lead by example. This is all a little bit confusing. One little thing I want to point out is that we're not just finding the displacement from a graph of velocity versus time, we need the initial displacement. Okay, so that's an important piece right here. The initial displacement. So that's a little bit different from how we worked in the other direction, going from displacement to velocity. This time we need a new piece of information. So a ball starts at x of 0 equals 2 meters and has the velocity v of t shown below. Where is the ball at A, 2 seconds, and B, 5 seconds? Okay. Well, it has a nice constant velocity over this time interval, and then it abruptly changes direction and has another nice constant velocity over this time interval. And so you'll see that that's almost a precondition for being able to solve these without using any calculus. All right, let's find the displacement as a function of time. So initially, let's actually begin work on our answer. X at 2 seconds is equal to, it started at 2 meters. That was from the problem statement. X of 0 is 2 meters. Well, it doesn't stay there. It's moving to the right at 3 meters per second. And so how do we determine the displacement or the change in displacement from 0 seconds to 2 seconds? Well, it was moving at 3 meters per second, and it was moving at 3 meters per second for 2 seconds. So what I'd like you to think about, you could just multiply those together, but I would like you to think about it as the area under this curve here. Okay. So it's moving to the right at 3 meters per second for 2 seconds. The height here is 3 meters per second. And the width is 2 seconds. And so it is in fact the area under the curve. And then that's 6 meters per second times seconds. So that's 6 meters. So we take our 2 meters, our initial displacement, and we add 6 meters. And that gives us a total displacement of 8 meters. That's it. That's the answer to part A. Part B asked for the displacement after 5 seconds? Well, I'll clean this up a little bit. So what you want to do is you want to find the net area under the curve from 0 seconds to 5 seconds. And so what that means is that we need to include this area up here. So I'll show you what that looks like mathematically. It starts initially at 2 meters. Then after 2 seconds, it's gone to the right by 6 meters. And so we add 6 meters there. That's what we covered in part A. And then after that, it abruptly changes direction. Now it's moving to the left at 2 meters per second, and it does so for 3 seconds. Okay, and so this height here is 2 meters per second. I'll say it's negative 2 meters per second. And the width is 3 seconds. Okay. Multiply those together to get the area under the curve. And we get area equals -2 times 3 equals -6 meters. That's its displacement from 2 seconds to 5 seconds. So we add that -6 meters. And we get 2 plus 6 minus 6 is 2 meters. So it happens to end up back where it started. All right, and that's it. That's parts A and B. One thing that I'd like you to see is that because the velocity is constant over this time domain, the displacement is increasing at a linear rate. So it increases by the same amount with each second or with each instant in time. And so the slope of the tangent at any point here on a displacement versus time graph will be the same value. Let's see what that looks like. So you're just going to take the results of the previous problem, and I'm just going to graph them. So it starts out at 2 meters, and then at 2 seconds it has risen up to 8 meters. And then at 5 seconds, it drops back down to 2 meters. So we'll connect all of those with straight lines. This time they are straight lines because the velocity was constant over each of those time domains. And this is our graph of displacement versus time, which we found from our graph of velocity versus time plus the initial displacement. If you were to take the slope of the tangent at any point along here, I hope that you see that you get a constant value. That's our 3 meters per second. And if you were to take the slope of the tangent at any point along here, it would give you -2 meters per second. Okay, so how about velocity from a graph of acceleration? Again, I hope you're seeing a pattern because every time we've solved for one, it's been directly analogous to another. So we can use the exact same procedure to determine the instantaneous velocity using a graph of acceleration versus time. The velocity is the net area between the A of t curve and the horizontal axis plus the initial velocity. Again, the horizontal axis corresponds to acceleration equals 0 meters per second squared. All right, here's an example. A rocket begins its flight with velocity v0 equals 3 meters per second. We'll say it's moving upwards. This is a little bit interesting. It's already moving upwards at the start of the problem. And has acceleration a of t shown below. So all you're given is this graph of acceleration versus time. I'd like you to find its velocity at all times. It's not entirely clear from the problem statement, but I really mean find its velocity at 1 second, 2 seconds, 3 seconds, 4 seconds, and 5 seconds. Okay, so let's start with something that's trivial. V of 0, what's the velocity at 0 seconds? Well, you're not going to get it from the graph. You're going to get it directly from the problem statement. V of 0 is 3 meters per second. That's our velocity at 0 seconds. V of 1, or 1 second, Now it's a little bit non-trivial. So it was initially going at 3 meters per second. But then over this 1 second, it was increasing by 15 meters per second each second. So 15 meters per second squared. And as we did before, we'll find the area of this little piece. The height is 15 meters per second squared, and the width is 1 second. The area is 15 meters per second squared times 1 second, which is 15 meters per second. Those seconds are going to partially cancel. And so that's 15 plus 15 meters per second. And when we carry out that calculation, we find that it's moving at 18 meters per second after 1 second. There's the velocity after 1 second. Okay. After 2 seconds, it continues to accelerate at that constant rate. And again, the area of this new square, of the second little square that I've filled in, is once again 15 meters per second, because it's 15 meters per second squared over a time interval of 1 second. And so we need to find velocity at 2 seconds. This is the cumulative velocity, and so it started its travel at 3 meters per second. Over the first second, it added 15 meters per second. And then over the second second, it added another 15 meters per second. So we add those all up, and we get 33 meters per second. How about the velocity after 3 seconds? Well, I'm getting tired of breaking this up into little squares. You're welcome to do that. You would just draw in another square to encompass this region here, up to 3 seconds. But I could just as easily fill in just this this entire region. So the height is 15 meters per second squared again, and the width is 3 seconds. And so the area of this rectangle is the width times the height, 3 times 15, which is 45 meters per second. So what does this look like on paper? V of 3 equals, initially, 3 meters per second. Always add in the initial velocity. And then add to that the 45 meters per second that it gained over those 3 seconds. This gives us a peak velocity of 48 meters per second. All right. After this point, it has a negative acceleration. It begins to slow down. As I said, in one-dimensional motion, accelerations are always associated with speeding up or slowing down, a change in the speed of an object. And so what we can do, we could have done this to solve any part of the problem, but I'd like you to know that there's just a few different equivalent ways of solving these types of problems. We're going to look at the net area under the curve from 0 seconds to 4 seconds, and so it'll be this area, or the initial velocity plus this area, and then minus this area. Why minus? Well, because the height of this is negative 10 meters per second squared, and the width is 1 second. And that means the area is negative 10 meters per second. Well, we already found the velocity up through the first 3 seconds, and so this is yet another way of doing this. v of 4 seconds is equal to the velocity after 3 seconds plus the new area. And the new area was negative 10 meters per second. Right? So up to this time, it's traveling at 48 meters per second, and then as it accelerates over this time, after it accelerates, it will lose 10 meters per second. Okay? So this is 48 minus 10, which is 38 meters per second. Just one more. Velocity after 5 seconds. And I'll do what I did in the previous one, where I'll just add on this new area. So it has a width of 1 second and a height of, again, negative 10 meters per second squared. This is equal to the velocity after 4 seconds plus the velocity that it lost over the 5th second, or over the last second. So minus another 10 meters per second. In fact, I didn't show the calculation, but the area is, again, negative 10 times 1, which is negative 10 meters per second. And so that's, previously it was traveling at 38 meters per second. So 38 minus 10, which gives us 28 meters per second. And that's it. These are the velocities at all time, and we determined it from the graph of acceleration versus time, plus the initial velocity. We needed the initial velocity in there. As we did before, we can graph these. So initially, it was traveling at 3 meters per second. And then after 1 second, it was traveling at 18 meters per second. And after 2 seconds, it was traveling at 33 meters per second. And after 3 seconds, it was traveling at 48 meters per second. It's a little bit difficult for me to graph this, but I think these are approximately correct, at least. And then it lost 10 meters per second with each second. So it was at 48 meters per second, and then decreased to 38 meters per second, and then it decreased to 28 meters per second, right around at 5 seconds. As usual, as we did for the previous part, we're going to connect these with a straight line because the acceleration was uniform over these 2 time intervals. Oops. And so if I've done this perfectly, the lines that I draw will go through the points that I've drawn. It looks like I'm a little bit low on this one, so I'm going to be sneaky and just move it up. Say that I graphed the wrong point. And yeah, take a look at this graph and convince yourself that if you were to take, this is velocity versus time, so if you were to take the slope of the tangent at any point in this region, we'll get an upward sloping constant slope. And that corresponds to this constant value for the acceleration here. And if you were to pick the slope of the tangent for this downward sloping region here, you'd have a constant negative slope, and that corresponds to this constant negative acceleration that you see right here. Just trying to clean up this graph a little bit for you. Yeah, constant negative acceleration right here. So that's it. That's our graph of velocity versus time derived from a graph of acceleration versus time. All right, let's look back at the 2 problems that we've gone over up to this point. So we had a nice constant velocity here, and then a constant velocity here, and we found this this graph of displacement versus time as a consequence of that. We did the same thing where we found velocity from a graph of acceleration versus time. We had a constant acceleration and then a constant acceleration, and we found this nice constant velocity. Does the velocity, when we're working towards displacement, does the velocity need to be constant? When we're working towards velocity, does the acceleration need to be constant? No, of course not. Velocity and acceleration are free to change. And so, what about other curves? So in both of the previous examples, the velocity and acceleration were given by straight horizontal lines. So they were constant over certain time intervals. What if the velocity or acceleration is not constant? Well, we can still approximate the area under the curve by dividing it into a series of very thin rectangles for which the velocity or acceleration is nearly constant. What does that look like? Well, suppose this is our graph of velocity versus time, and I want, the displacement up to this point. So we'll find the area, or the net area under the curve. So I want the displacement up to this point. What I'm going to do is I'm going to chop it up into a bunch of little rectangles, like so. They're not rectangles yet, they're just lines. And continue to divide it. Okay, and if I've done this fairly carefully, I can now create the actual rectangles. And take a look here. The velocity over each one of these time domains, over each one of these rectangles, is nearly constant. Previously we dealt with velocity that was explicitly constant. Now we're dealing with velocity that's nearly constant. And I mentioned that you're trying to find the area under the curve. I hope that you agree that this is a close approximation to the area under this curve. Okay, so here's what you're actually going to do, or what you would like to do if you could. So what you would like to do is to just find this area under the curve minus this area because it's below the horizontal axis. So this counts as a negative value here. And that will give you your displacement up to that time. Well, that procedure that I just went over, where you chop it up into a bunch of little rectangles and you then add them all up to approximate the area, that's integration from calculus. If you've taken calculus, then you may remember that. If you're just starting with calculus, then that's what you have in store for you. And if you haven't taken calculus, don't worry about it. Just be aware that, hey, you can just chop something up into a bunch of little rectangles, and that will allow you to approximate the area under the curve, which is what this procedure is. And of course, this works just as well if I ask you for the velocity as a function of time from a graph of acceleration versus time. So if I gave you a of t instead and asked you to find velocity, which used the same procedure, finding the area under the curve. In summary, putting all of this information together, if you start with a graph of displacement versus time, and then what you can do to find velocity versus time is take the slope of the tangent of that graph. And if you have a graph of velocity versus time and you want the acceleration versus time, again, you take the slope of the tangent to that graph. That gives you acceleration versus time. If you start with acceleration, with an acceleration graph, you find the net area under the curve plus the initial velocity. That gives you velocity versus time. And if you start with velocity as a function of time, a velocity graph, then you can find the net area under the curve plus the initial displacement, and that will give you your displacement versus time. Pretty straightforward, I think. This is a very handy kind of summary to have on a note sheet, so I would highly recommend writing it down. I would recommend having it close at hand. And if you're allowed notes on your exam, yeah, this is a nice little thing to put on your cheat sheet for the exam. But really what I want you to take from this video, if nothing else, is this last equation, which is really going to kind of open up quite a bit of new material for the class. So net displacement is the average velocity times time. The most useful piece of information we can learn using these techniques concerns the net displacement over a time interval when acceleration is constant. So we'll show that when acceleration is constant, the net displacement is equal to the average velocity times the time interval. What does that look like? Well, here's a graph of velocity versus time. The velocity, I've drawn it, going to 0 outside this time interval. It doesn't have to. It could, do something like this outside the time interval. Doesn't really matter. It can't double back on itself like I've kind of drawn there. So pretend that this is vertical here. But the point is that the velocity is increasing at a uniform rate over this time interval, and this is the time interval that we're interested in. We don't care about what it's doing outside the time interval. Okay. So what is the displacement over this time interval? Well, it's equivalent to asking what is the area under this curve. Well, I haven't given you a whole lot of whole lot to work with, or you do have all the information that you need to solve this, but you may not remember the formula for the area under a trapezoid. This is a trapezoid kind of laid on its side here. It has two parallel sides, so it's a trapezoid. If you don't remember the area for a trapezoid, then you have to be graphically a little bit creative, or at the very least take it to someone who knows a lot of math. So how do we find the area under this trapezoid? Well, here's what I suggest we do. I'm going to suggest that we go straight for the midpoint of this velocity versus time curve here, and chop off this triangle up here, and we're going to move it down here. All right? So, oops. So, we've chopped off that triangle, and we've replaced it down here. So, this piece up here, I want you to just ignore. And this piece in here is now filled in. All right, well, what is the... I hope that you agree that by doing this, by just chopping off this triangle here and moving it, we haven't changed the area at all. It's still made of the same pieces. Those pieces have just moved around a little bit. So the area under this new curve, oops, the area under this new curve right here is equal to the area under the trapezoid that we started with. So all that we really need to do now is to determine the height of this. Well, the velocity was increasing at a uniform rate, which means it had a constant acceleration. That's very important. It has to be increasing at this linear rate for this to be true, for what I'm about to say to be true. And for us to be able to swing a triangle around as we did. And where we're going to, the height of the rectangle that we're looking at is going to be the average of these two velocities. V initial plus V final divided by 2. Okay. So it should be halfway between these two, and you can pretty quickly work out that, if you take this value here, it's going to be halfway between V naught and V final. All right. So what's the area? The area is x final minus x initial. So for those of you who are wondering how I got x final minus x initial, I'm just using the fact that x final is equal to x initial plus the area. Okay, so it's just a little rearrangement of what we saw earlier in this video. So I just subtracted x initial from both sides. So x final minus x initial, the net displacement, is equal to the area of that curve, which is equal to V naught plus V final, oops, divided by 2. That was the height right here. And multiplied by the width of the time interval, t final minus t initial. All right. So again, let me write this out fully explicitly. X final minus x initial is equal to v naught plus v final divided by 2 times t final minus t initial. All right. This is a very important equation. It only applies when the acceleration is constant. If the acceleration is not constant, then the average velocity does not manifest itself as v naught plus v final divided by 2, or v initial plus v final divided by 2. But what we'll be concerned with for basically the remainder of the course up through Newton's laws, and in fact even much of the course beyond that, is constant acceleration. And so when we have constant acceleration, we can apply this formula, and we have one other formula already. I'll tell you what that is later. But we have one other formula already that applies under constant acceleration. And with these two formulas, we can derive two more that also apply under constant acceleration, and those will comprise what are called the kinematic equations. And so we'll have 4 equations to work with. That'll be the topic for next video, but like I said, that's going to kick off a lot of the mathematics of this course. And mathematically, I will just warn you that the course is about to get a whole lot more difficult. And this is where it starts, where it begins. So run through that derivation maybe a couple more times until you're comfortable with it, and be prepared to use this equation along with several others moving forward. So good luck with that, and I'll see you in the next video. Bye bye.